discussing Pythagorean mathematics and philosophy. And as we see over here to the right side of our screen, this is a painting named The School of Athens by Raphael in the early 16th century. And in the bottom left corner of this picture, we have Pythagoras. And we zoom in and we can tell that Pythagoras is writing something down. It is believed that this is something to do with harmonic ratios, but of course this is uncertain. However, this picture depicts a little bit of irony, as Pythagoras and his followers almost never wrote anything down, as everything was orally transmitted. And then we jump back and we see the Plimpton 322. It's called the Plimpton 322 as its catalog number 322 in the George Arthur Plimpton collection at Columbia University. This tablet is dated between 1900 BC and 1600 BC. And of course, this is significant because the Babylonian mathematicians were aware of the Pythagorean theorem roughly 1,000 years prior. We look at this timeline where we see the Plimpton 322 dated between 1900 and 1600 BC, and Pythagoras coming over 1,000 years later. And then, of course, Euclid's Elements 200 years after Pythagoras himself. So, of course, we do have the Plimpton 322. It is currently at Columbia University, as mentioned, but we have a picture here, and we can see that it's divided into three distinct columns. The left side column has a header that translates to width. The middle column has a header that translates to diagonal. The right side column does not have a header, but it is obviously believed to be a numeric sequence, 1 through 15. As we see, the History of Mathematics textbook has translated this tablet for us, and this tablet is very debated. There are a few skeptics, not many, that will try to state that these aren't Pythagorean triples. These are simply solutions to quadratic equations, but many will believe that these are Pythagorean triples. As we notice, we have the 119 as the width, the 169 as the diagonal, and all we are missing would be the other leg length of 120. It is likely that this 120 was calculated. It could have been broken off the tablet, or it could have just not been included on the tablet. We're not really sure. The method of which the Babylonians used to calculate these triples is also heavily debated. However, in the early 1960s, de Sola Price did come up with a very strong argument in his case, as it seems that there were 38 lines in total, and numbers 16 through 38 were kind of left blank. He kind of set a limit on the values, and it seems to make sense regarding his numbers. The issues with the tablet are a few errors, and these look like huge calculation errors. However, it seems as though these errors are more of a scribal error. For instance, for row number 9, we have that 769 as the diagonal, and the correct width would be 481. However, the Plimpton 322 is translated to be 541, which of course would be a miscalculation. However, many believe that this is simply a scribal error because of how the Babylonians wrote. 541 is a 9, 1, and 481 is a 8, 1. So it seems as though there was some type of scribal errors on many of these that have parentheses. Now we look at Pythagoras himself. Pythagoras was a very influential man in circa 500 BC. He founded the school of Pythagoras. A famous line by Pythagoras and his followers is that number is the cause of all nature. Pythagoras had no written works that are found, but he is credited with the first rigorous proof of the Pythagorean theorem. This idea that number is the cause of all nature leads us into math mysticism. Pythagoreans, which were followers of Pythagoras, believed that numbers were assigned to everything spiritual or physical. And of course, in saying numbers, they're meaning positive integers. Another famous line by Pythagoreans is all is number. This is extremely significant because it's the first introduction of parity, evens and odds, which of course then leads us into the beginnings of number theory. This idea that numbers are assigned to everything spiritual or physical, here are a few examples. 1 symbolizes reason, as reason can only produce one constant body of truths. 2 is a man, 3 is a woman, 4 is justice, as it is the first number produced by two equals. 5 is marriage, as it is the combination of man and woman, and 6 is creation. And the idea of even or odds come into play as most evens were considered to be feminine after the number 3, and most odds were considered masculine after the number 3. And then we get to look into Pythagorean numbers. So this idea that numbers are everywhere led many Pythagoreans to create systems of numbers. For instance, we have triangular numbers, where we arrange dots to where it creates an equilateral triangle, like so. So some triangular numbers are 1, 3, 6, and 10. Likewise, we have square numbers, where we have 1, 4, 9, and 16. And with this creation of numbers and symbols, we can then find patterns within this. So one pattern that was observed is that two consecutive triangular numbers will add to give you a square number. For instance, 1 and 3 will give us 4, 3 and 6 will give us 9, 6 and 10 will give us 16, and so on. So as mentioned, there is not a written proof by Pythagoras himself, but it is believed that either him or one of his followers at the school of Pythagoras came up with an idea of a proof for the Pythagorean theorem, which it would be later named. The start of this proof is that there are four congruent right triangles, like so. And then you maneuver these four congruent right triangles into a square with side length a plus b. And then it can obviously then be seen that we have two leftover squares of area a squared and area b squared. And then we construct another square congruent to the initial square with a plus b as a side length. And we bring in the four congruent right triangles just the same, but we configure them differently. So now the leftover area here would be c squared, as we have a square of side length c. And by setting the leftover areas equal, we're given the famous Pythagorean theorem a squared plus b squared equals c squared. With area proofs, such as the previous one, it is believed that there are many proofs that are just not found that predate Pythagoras. One of those examples is the Chinese Koku theorem. It's depicted in the diagram. It is found in Arithmetic Classic of the Gnomon and the Circular Paths of Heaven, which is the oldest Chinese text containing formal mathematical theories. The oldest parts of this could be circa 600 BC. Mascara II, who was born in the early 12th century, was inspired by this and he created another construction. He actually published this in Vijayanagara, which is, in English words, root extraction. In this, he simply drew the construction and wrote "Behold" and left the rest of the proof up to the reader. The construction looks something like this. We start with a square with side length c. There are 4 congruent right triangles within this square, setting the hypotenuse to the outside. The inner square has side length of a minus b. We then move these shapes around to get a square of a minus b with a rectangle of sides a and b and another rectangle with sides a and b in this fashion. Doing a little bit of algebra, we want to solve for this side length. A minus b plus b is simply a. And a minus b is simply b, as shown. And now we change our perspective a little bit, and we can see that we have a square of a and a square of side b. And we take a look at our original square. These shapes make up both of these areas, so we can set the areas equal to each other, and we have the Pythagorean theorem, a squared plus b squared equals c squared. Now looking at a slightly more modern proof of the Pythagorean theorem performed by President James Garfield, who was not at this time a president. The year's 1876 when his proof got published to the New England Journal of Education. He's serving on the House of Representatives. The proof starts with 2 congruent triangles of legs A and B and hypotenuse C. The triangles are stacked on each other's vertices, and a line is drawn from the opposite vertices. We now have a trapezoid composed of 3 right triangles. If the area of the trapezoid is composed of the area of these 3 triangles, their area must be equal. The area of the trapezoid is 1/2 times a plus b times a plus b. The area of the 3 triangles are 1/2 a times b plus 1/2 a times b plus 1/2 c squared. Setting these areas equal, we're allowed to do a little bit of algebra and multiply both sides by 2. And now we can FOIL out the left side and combine like terms on the right side. And now we can see that we have 2 ABs over here and 2 ABs over here. These will cancel. And what we're left with is the Pythagorean theorem, a squared plus b squared equals c squared.
And so now we'll look at Pythagorean mathematics influence. So we'll start with the Greek influence on the ancient world. So we see a shift towards theoretical mathematics, which is different than the normal at that time, which is only practical math, such as construction, accounting, and surveying of land, etc. The phrase all is number led Pythagoras to find that there are number ratios, integer ratios, within music. Equally tight string, there's a certain ratio to where the notes are more beautiful. He found the octave, the fourth, and the fifth. This idea was later defined by Marine Mersini as harmonics in the early 17th century. And this ties to the music of the spheres, which is where there are inaudible sounds coming from our planets, which at this time there were only 7 known planets. And Pythagoras himself claimed that he could hear the sound while no one else could. This is one of the many supernatural characteristics that have been given to Pythagoras, as Pythagoreans only shared things through word of mouth. The Pythagoreans also emphasized the importance of proofs and rigor, and as mentioned, it is the beginning of the number theory. The modern influences are things like trigonometry identities, which is simply the Pythagorean theorem applied to a unit circle. Things like Fourier analysis, which stems directly from harmonics, and the distance formula, which is very easily derived from the Pythagorean theorem itself. And we can see the distance formula in technology today like GPS. And then, of course, the modern day influence is Euclid's Elements and modern day proofs. This level of rigor is something we still use to this day